So the next thing we should discuss is how we can actually learn a PCFG from data. And as I described earlier in the course, we have resources available called tree banks, which are extremely useful for this purpose. So an early and very famous example of a tree bank is the Penn Wall Street Journal tree bank. And tree banks consist of sentences. Here we have a 30-word sentence, together with their underlying parse tree. And these parse trees are actually annotated by hand. So for example, in the case of the Penn WSJ tree bank, a group of people in the early 90s at University of Pennsylvania got together and came up with a set of conventions based on linguistic theory for the form of these structures, and went through and annotated 50,000 sentences. That's close to 1 million words of data. So we actually have example parse trees from which we can learn the rules and parameters of a PCFG. The Penn WSGA tree bank was one of the earliest examples, but by now we actually have many different resources in many different languages of this form. So once we have a tree bank, learning a PCFG is actually extremely straightforward, almost trivial. So there are two things we really need to learn. One is the set of underlying rules in the context-free grammar, and the probabilistic context-free grammar. So we might, for example, learn a few rules like this. And the other thing we need to learn is parameters associated with these rules, for example, 1.0, 0.6, and so on. In terms of the rules in the PCFG that we learn, we simply take all rules seen in the tree bank. So learning, quotes, learning the context-free grammar is simply a matter of reading off the rules in the tree bank, reading off the context-free rules. How do we estimate the parameters? So remember, Q of some rule alpha goes to beta is the probability associated with that rule. We're again going to make use of maximum likelihood estimates, which again have a very simple and intuitive form. And so to estimate the parameter for some rule, alpha goes to beta, we take a ratio. So on the denominator we have the number of times we've seen alpha, and on the numerator we have the number of times we've seen the entire rule. So for example, QML of VP goes to VT NP would simply be count of VP goes to VT NP divided by count of VP, where these counts are taken very directly from the example trees in the tree bank. There are various guarantees for these kinds of estimates. This is one important one. So if the data we're looking at, if the tree bank is actually generated by some underlying PCFG, you can show that as the training data size gets larger and larger, these parameter estimates will get closer and closer to the true underlying probabilities in the PCFG generating the data. And that leads fairly directly to a property that the distribution over entire parse trees defined by our PCFG that we learn converges to the correct underlying distribution under the PCFG, which is generating our training data. Bottom line though, given a tree bank, it's very easy to learn a PCFG. We simply read off the rules from the tree bank, and then we calculate these maximum likelihood estimates, which amounts essentially just to counting the number of times we've seen non-terminals and counting the number of times we've seen entire rules. So I just want to talk about one final technical property of PCFGs. This goes back to work by Booth and Thompson from the early 70s. So if we step back and think about what we've done, it's really rather remarkable. So if we take a given CFG, there will be some set of well-formed parse trees under that CFG. So we have some set of parse trees. These are quite complex structures. And in fact, for many CFGs, this set will be infinite. So actually, for the CFG I showed you earlier, there are actually an infinite set of possible trees. We now have a way of calculating a probability for each tree under the CFG. So for example, this might be 0.01, might have 0.00057, 0.004, and so on and so on. And we've done this by simply assigning a probability to every rule in the CFG, and then for a given tree, we just multiply together the rule probabilities within that tree to get this probability. So for this to define a correct distribution over possible parse trees, these probabilities have to sum to 1. So we're attempting to define a distribution over an infinite set and an infinite set of quite complex structures. So Booth and Thompson give conditions on the rule probabilities under which we get a proper distribution over trees. The first one is exactly what I showed you earlier, and it's by far the most important. And that is that if we take any non-terminal, for example VP, and we look at all of the rules with that non-terminal on the left-hand side, for example, we might have the following, then these rule probabilities have to sum to 1. Okay, so this would be valid, for example. That's the first condition. And that's really the only one you really need to worry about. I'll just briefly mention, though, that there are some other conditions which are rather technical, and we'll go over them very quickly, although they are somewhat interesting. So let me give you an example of a grammar which satisfies this first condition, but actually does not define a distribution over possible trees. So the rules in this grammar are very simple. S goes to SS, or S goes to A. And so we'll generate parse trees like this, or this one right here, and so on. And in fact, you can see there are an infinite set of possible parse trees under this grammar. And let's say I choose probability 1 for this rule, probability 0 for this rule. So this satisfies the condition that the rule probabilities sum to 1, but actually for any finite tree, this is going to get probability 0 because it has S goes to A in it. This is going to get probability 0 because it has S goes to A in it, and so on. So actually it's going to assign probability 0 to any finite tree, and it will fail to define a distribution over possible trees. Okay, so that's a simple example of a grammar that satisfies condition 1 but is ill-formed in some sense. A second example, which I'll just very briefly mention, is a little bit more surprising. You can actually show that under certain settings for these rule parameters, so if I say 0.6 for this and 0.4 for this, you can actually show that this grammar also fails to define a well-formed distribution over trees. You can show that the sum of probabilities for the set of finite sized trees actually sums to less than 1 for this particular case. And intuitively what's going here is the grammar is splitting too quickly, and it has probability less than 1 of actually producing a finite length parse tree. Okay, but I just wanted to mention that very briefly. It's sort of curious. In practice, this is never really a practical concern, but it's just worth having at the back of your mind.